Before you go away, you could introduce the next speaker.
Thank you. Is this still? Yes. The next speaker I would like to introduce is Professor Michael Spall.
Thank you.
Director of... No, you get a longer introduction than that. The director of UWA's Data Institute, and I must say, as well as an impressive researcher that we all know, somebody who is leading this institute and heading, and we can see the clear progress of that inculcation of the values that the Data Institute conveys being promoted at UWA, and it's great to see, and that's what he's going to talk about with AI, the authentic information. What does it mean for AI to think?
Thank you, Andrew. So I should start with one small minor trigger warning. Those of you that have listened to me speak before, you might have got used to several Donald Trump jokes at various points throughout my talk. Unfortunately, that topic is no longer particularly funny. And so I'll be avoiding all political jokes altogether. Who's seen this movie? Keep your hand up if you read the paper. The paper is actually really good. And from psychology to something published in the journal Mind in 1950. This is the original paper by Alan Turing where he proposes the imitation game. Okay, so I guess everyone here is more or less familiar with this, but this is the idea that if I get an audience member to speak to a computer or to a human being behind a screen, that they can't tell which is human and which is computer. Okay, so the idea that a computer could mimic conversation well enough to fool most people most of the time. We're kind of there, right? I mean, ChatGPT is not fantastic, and it is a bit repetitive, it is a bit long-winded, it gets stuff wrong quite often, it makes stuff up, but I know people like that too, so it's probably not far off human level, being able to fake it well enough to be human. But actually, I hope you can almost read that in the back there. This is part of that paper. Again, 1950. Turing says that in about 50 years' time, it will be possible to program computers with a storage capacity of about 10 to the 9. He doesn't say 10 to the 9 what, but we'll assume bits or words or something, and we're kind of there. Well, we're past there, actually. The original question, can machines think, I believe to be too meaningless to deserve discussion. So the topic of today's talk is, can machines think? Nevertheless, I believe at the end of the century, the use of words and generally educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. Yes and no. And I'm going to try and set out why I think it's worth contradicting that statement some of the time. But the main topic of what I want to talk about today is, what are we actually looking for when we're talking about machines being intelligent? What do we actually hope to get out of this? And what would be a good test of whether machines are doing something useful and intelligent? Who here has used ChatGPT or some other chatbot to talk to chat with? Oh, right up in the air, I can't see. Who's used it to actually solve a useful problem? Who's used it to do their maths homework? James? It's actually pretty good at a lot of these things. It's pretty good at solving standard mathematics questions. Integrate this, solve this differential equation, largely because it's trained on a corpus which includes a lot of similar things to what you're asking it to do, right? So it's already seen lots of similar examples. The risk, James, is that actually it will fake it. So if you ask it a question that it doesn't know the answer to, it'll pretend that it does. And it will try to convince you. It'll try to give you an answer that is as convincing as possible. But nonetheless, I kind of think that, well, there's two flavors to this talk. Originally, I was going to talk about how we could use mathematics to better understand AI, but actually a lot's happened with language models and what they can do in the last 6 months or so. So I've kind of changed my focus and instead looking at whether we can use these tools to actually do something useful mathematically. And of course, I'm interested in mathematics as a mathematician, but any other discipline, so you could ask similar questions. Mathematics, I do think, is a little bit special in that, at least some of it, in its axiomatic nature, there is a right and wrong answer, and you are looking for a machine to make deductive steps rather than, as we just saw in psychology, if you just make up a nice story and claim it to be true, people will believe you. That was what you were saying, right? Yeah. Well, at least you need to have a yes or no question. Things are true or they're not true. And this is where ChatGPT, and I'm going to use ChatGPT here as a synonym for all large language models, just because that's the one that I've played with. That's the one that I guess most people have at least seen. All of them are fairly similar. And this is an example of how ChatGPT does get stuff wrong. Not so long ago, if you asked it how many R's were in the word strawberry, it would confidently and emphatically reply 2. And it was only after some tweaking and encouragement that it actually got 3. This was an internet meme. Someone wrote a research paper to solve that problem. I did the opposite here, and this is a research paper that I got ChatGPT to write. This is entirely written by ChatGPT. For the mathematicians in the audience, I had a discussion with it. I proposed a model. I wanted to build a model of how information diffusion would be diluting useful information as chatbots increasingly pumped out garbage on the internet, and it built such a model. There are differential equations that it came up with to describe that model, describing the rate of increase of information, the rate of increase of useful information versus pollution from the AI itself, and it solves those equations. It gives me some graphs. Sorry, Alistair, that's possibly the stupidest bifurcation diagram I've ever seen, but it has a diagram and it claims it's a bifurcation diagram. It produces LaTeX for all of this. So for the mathematicians, so you don't even have to worry about that. It produces source code for the pictures. So you can reproduce the pictures, you can modify them. This one, it does have a predilection for long lists of things. And I guess that kind of a telltale here, but it also doesn't have references. Other language models are capable of getting references sorted out, but ChatGPT just tends to make them up, which is a bit of a problem. But it makes them up confidently. The weird thing about this was when I was having this, creating this paper, I was doing it as a dialogue with ChatGPT, much like I might with a particularly poor PhD student or honours student. Except instead of saying, go and do this, and then coming back a week later having done it, and then me saying, no, you did that wrong, do this instead, it was instant, right? So you get like 6 months of supervision in an hour and a half. So it's kind of interesting where it's going. So is it actually, what is it actually doing? Now, if you look at a lot of stuff on the internet around AI and generative AI in particular, you get sold a particular model on what exactly AI is doing. You get told that AI is just generating text, well, generative AI is generating a sequence of text by choosing a next word based on previous words that were likely. All right, so once upon a time, there is probably a pretty safe bet. That's what the next word would be. And just pick words after words after words. The punchline's coming, don't worry about that. And so building up one word after another word, you get a story. Of course, that's kind of a nice idea, but that can't possibly be how ChatGPT actually works, right? Because there's no way that you would be able to choose one random word after another random word well enough to come up with a story like that. I mean, in fact, a story like that is kind of hard to believe anyway, right? That was a joke. As I said, there's no political jokes because they just aren't funny, right? So what is it actually doing? Well, one way of thinking about it, sorry, the music's coming through here, but never mind. You could do the same thing with music. You've got a sequence of notes, and when you compose music, you're interested in what note comes after the previous notes, right? So you essentially construct a graph of those notes. Each note on the graph is a particular note, semiquaver B flat or whatever, and you put connections between those notes if you see them occur one after another in your corpus of text. And then you just do a random walk on that network to simulate music. So I can take entire corpus of Mozart's compositions, shove them into a computer as a sequence of notes, create a graph, just do a random walk on that graph, and I should be able to compose some more music, right? Well, for those of you that can listen, can hear it, this is what it sounds like. It's not that bad, you don't have to leave. Or rather, it is that bad, but it's going to stop soon. It's pretty awful. It's not completely inharmonic in that the notes following one another are kind of arranged in a sequence that makes sense, but it's pretty rubbish because it's just choosing one note after another. We did this back in 2010. My PhD student at the time wasn't so much a fan of Mozart. Does anyone recognize this person? This is a composition in the same way, except we've just embellished it a little bit. So we're taking some MIDI files, some computer files of music of Teresa Tang, Taiwanese pop artist, and recomposing it by recombining those notes. It's better. It's not great. It's certainly not Mozart. So my point here is that actually the idea that generative AI is just creating notes one after another by looking at the previous ones and picking the next one is kind of missing the point. Because we did that, doesn't really work. That's enough. And you can go and prove that, and the only reason I put this up here is because I'm quite proud of the title of the paper. In it, we looked at Bach's music and compared it to a randomly chosen sequence of notes, which is technically a Markov chain, and asked is there statistical difference in it, and not surprisingly there was. We went in the paper a bit further to understand exactly what's going on there, but essentially just random sequences of notes is not enough. So what are we doing? Okay, so this is where the second trigger warning comes in. There's a little bit of maths in this talk, not too much. The first thing we need to think about is some idea of an embedding. So we need to have a parameter space. So we have variables. Here I'm just showing two variables. On one axis, education level of the average voter by political party. On the other axis, average income of the average voter by political party. And so that gives me, for both major parties in the US, two numbers. That gives me a point coordinate in two-dimensional space, and I can track how that moves over time, right? So you can see that over time, the point moves from down here up to this direction. So it's moving from low education, low income, to high education, high income, and the other one's moving in the opposite direction. So what generative AI does is a similar sort of thing. it provides coordinates for the state of your thing of interest. In this case, a word. Doesn't have to be a word. Mathematics might be a logical construct, but for here, time being, it's a word. But instead of doing it in 2 dimensions, we do it in very, very many dimensions. And the way in which we do it is we construct an embedding, but not an embedding to 2 dimensions, an embedding to maybe 300 dimensions. So for each word, I associate 300 numbers that describe the qualities of that word. And the way in which I do that, well, there's one way in which there's a couple of techniques shown on the slide here. Basically, I'm trying to build a model that, given the input on the left, there were old men, predicts the output too as a likely word to be associated with the words on the left. Right, so it's looking for what words are likely to be associated with those words on the left. This is the math slide I warned you about. Essentially, I start with, and I will skip through it to pictures at the end, so if you don't like equations, just think of Teresa Tang for a few minutes and we'll come back to the pictures in a second. Essentially, the input, the words, if I've got a language of 100,000 words, each word starts off as a vector in 100,000 dimensions. It's a vector that is all zeros except for 1, 1. Word number 1 has a 1 in the first place and then 99,999 zeros. Word number 2, 0, 1, and then a whole bunch of zeros. Right? So it's all zeros except for a 1. The position of the 1 indicates the number of that word. It uniquely identifies that word. So you're uniquely identifying your words with points in 100,000 dimensions where the coordinates of the points are all zeros or ones with just 1, 1. A really dumb way of representing stuff, but sufficient. We then construct a projection, and the projection is this part here where I'm multiplying my word, wi is that vector in 100,000 dimensions. I multiply it by a matrix to get something in 300 dimensions. So this is simple, very simple matrix algebra, but a huge matrix multiplied by a huge but very boring vector to get a slightly smaller, more interesting vector. I then combine those vectors, that's the summation sign, and the output layer, the second part down here, I'm then squishing them down so that I get numbers that represent probabilities. That's all that needs to do. And it makes it a tiny bit nonlinear. To do all of this, I need to figure out what U should be. Now, U is a matrix, it's a big matrix. I've got 100,000 different words, and I want to project down to 300 dimensions. So it's 300 times 100,000 numbers. Right, so what's that? 30 million numbers. And then there's another matrix W, which is kind of the opposite of U, which is another 330 million numbers. And the first part of cleverness is that I train, well, not me, but clever computer scientists, train an algorithm to estimate what that U and that W should be. And when you've done that, what you end up with is an embedding of each word that tells you for that particular word, and I'll give you a list of 300 numbers that define the qualities of that word. So the whole process of the picture is this. I start on the left with my words. Each of them is a vector in 100,000 dimensions. That's zeros and ones. Multiply it, pre-multiply it by a matrix U, which is a massive matrix, to get a vector of 300. Sum them all up. That gives me my latent space. Multiply by the opposite matrix to get back to my prediction of what the in-between word should be. And the machine learning here is fitting the U and the W. It's determining what those embedding parameters should be. Okay, there is a second, so that's the first piece of the secret sauce of how large language models work. They provide a useful, coherent embedding of words where there's meaning in those numbers. So the numbers carry meaning about the words. The second part I will skip over. Actually, I'll get to that in a minute. So what does that look like? I'm going to draw it in 2 dimensions here. And I've used the word shyster just because I've always wanted to use the word shyster in a public lecture in front of other people. Think of your favorite untrustworthy occupation. I won't label it. If you go to that link down the bottom, you'll get a list of occupations in order of trustworthiness from most to least. But substitute shyster for that occupation in your mind, just so I don't offend any lawyers. I mean, anyone from that occupation in the room. Actually, it's social media, what are they called? Influencers. It comes out top for some reason. So if I think about the word shyster in 300 dimensions, it's got a point in 300 dimensions. And the word deceitful is a point in 300 dimensions. I can work out the vector connecting those 2 points. That's just high school vector calculus, right? Vector algebra. One vector minus the other vector. I could think of another word, different occupation, hypothetical. I could think of a different other word. And I could construct the vector connecting those 2 words. And it turns out, because of the way we've chosen to embed these words, if those pairs of words bear the same relationship, then those vectors will be close to the same, similar. So you can then you can do algebra on this, right? So these are points in 300 dimensions. If I take the deceitfulness from the shyster and add insightfulness, I get a professor. Right? But that's just moving these 300-dimensional numbers about. The link on the top, by the way, is a web app where you can go and see in real time what the actual embeddings for these words are. It's also a standard package in Python and all the languages. You can get this stuff easily enough. So this is the first part of the secret sauce. I've got a way of taking my words and creating lists of numbers for each word where the numbers actually mean something. The second part of the process is a little more complicated. Second part, I'm not going to explain this in full because I don't understand it, to be honest. And I've not really found a really good explanation of exactly what's going on here. But you take your sentence, you create tokens representing those individual words, you embed them in that 300-dimensional space. Think of those little dots connecting things together. We add some information about the position of the words within the sentence, and then we perform many layers of neural networks. The layers here, the transformer layers, are essentially a whole bunch more of matrix algebra. It's more of those U and the V and W matrices from earlier. Except they are built in such a way that the different layers give you different information about the sentence and how it's structured. And it also provides you with information that encodes the position, the relative position of the words within the sentence, so you get a kind of hierarchy view of the whole sentence. Right, so that's where you get from just knowing about an individual word and asking what comes next to knowing about the whole sentence and knowing that you are trying to solve a high school algebra problem and that you've got to follow several steps to get to the answer. Okay, so that's the basic technology. Important thing to notice here is that it's relatively easy to compute. I'm personally interested in computing networks, neural networks where you have recurrence, so your connections are looped together. In mathematics, we construct these randomly because we're not clever enough to optimize the parameters. In computer science, instead of optimizing the parameters of recurrent networks like that, they tend to find architectures that are smarter and layered, so you don't have to go through that. So you can use things like backpropagation as a technique to fit all these parameters. So it becomes a straightforward computational task to just do to fit the parameters. You're fitting lots of parameters, and those parameters, that's what people are talking about when they say this is a 90 billion parameter model or 150 billion parameters. That's the number of numbers in these matrices that you have to fit. So 2 things that we're going to use: the embedding to get the coordinates of a word with meaning, and then something that is encoding the relationship between the words, putting it in layers so that the different layers of the network relate different information. But can it do something useful? And by useful, I mean maths. So it wouldn't be a talk about generative AI without a couple of AI-generated pictures, right? So this is the first one. I'm going to give basically 4 examples of the ways in which people have been or are going to be or are using AI techniques to do mathematics. And don't be hung up on mathematics. That's just my obsession. You can substitute whatever you want to in there, in many cases. First, I'm not going to talk about the generative AI, the stuff that I've just been talking about, where we're trying to generate sequences of words. I'm just going to talk about traditional machine learning. Think of traditional machine learning as I've got a collection of possible components for my model, jigsaw pieces, and I'm going to pick up the pieces of the jigsaw puzzle that I want, arrange them in a particular way, but also I have the option of not using all of them. That would be overfitting. So I'm using my jigsaw puzzle pieces, combining them in some way to produce a model. The model is the output of that process. The training is where the monkeys come in, because essentially these problems are very difficult to optimize, and the best way mostly are just random search of some sort or other, optimized in some way. Okay. The second part of it is that once I've used machine learning to find this optimal, and it's a local optimum, it's not a global optimum, but it's just a particular, it's a goodish model, then how does the model, that machine learning, become useful? It becomes useful if we can explain something about the underlying process. Let me be a bit more concrete and give you an example. I could have a system where I can observe over time the state of the system. So on the horizontal axis I've got time, and I'm measuring the amplitude of the system over time. This is just like Andrew's example, except because I've used a computer to generate it, I've got a lot more data. I've got 3 variables. Andrew had a few more variables. His variables were numbers from 1 to 6 or something. My variables are real numbers, and I can measure them a lot more frequently. I have the luxury where I'm not just surveying a person every day and going to annoy them. I can survey them at 50 hertz and they won't get annoyed. They'll just keep giving me the numbers. But I don't know what the system, well I do, but let's pretend I don't know what the system that generated these equations are. A simple way of applying machine learning would be to build a model that generates those equations. Right? And this is what Alistair did. When was it, Alistair? 2002. So this is essentially machine learning to uncover the parameters of a model. I've got my model, I've got my data, I put it into the machine and it tells me what the differential equations are. Right? It's telling me that to describe that particular model, I need 3 equations, x, y, and z. They're first order differential equations. The x dot equation has a y is 10 times y minus 10 times x, and then there's 3 very small terms. So that's saying x dot is equal to 10 y minus x. Okay? The y equation, y dot is equal to minus y minus xz, 28x, and 2 very small terms. And that turns out to be correct, apart from the very small terms. The very small terms are there. They're not actually an error. The very small terms are there because we're integrating over a finite step size, and you have to account for the fact that Euler integration isn't doing what it's supposed to do exactly. Well, it's not exactly correct, right? So they're the correction terms for that, approximately. But this technique, 2002, allows us to pick out the equations from just data, right? There's a lot of more recent progress in this because computers have got bigger and faster, and people are able to do this much more effectively and efficiently. But actually, to be honest, the claim is that if we do this, we can get equations which we can use to understand the model. But mostly the scientific literature hasn't really done anything useful with it. Right, it's just used it like we did in 2002 to show that you can get these equations from the data. But interestingly, the one place where people have actually done something useful with this kind of idea is in pure mathematics. So pure mathematics, you have a lot of problems where you're trying to associate one object with a different object, right? So you want to make a connection between graphs and polynomials. Doesn't matter if you don't know what these words mean. You might want to make a connection between knots and finite simple groups. I'm making this up. Any group theorists in the audience, you can argue with me later. But you want to connect these different objects. One way to connect these different objects is to construct a function that relates the object of type 1 to the object of type 2. So you want to construct a function that turns your graphs into, what did I say they're going to be? Polynomials. Yeah? Is that what I said? Yeah. So you want to construct a function that turns a given graph into a given polynomial. You've all done this when you've tried to log on to Gmail or just about any commerce website where you've been presented with a bunch of pictures of handbags or gates or bridges or bicycles. There's an unhealthy obsession with handbags and bicycles in the machine learning community, but you've got these objects and you're trying to differentiate them between them. Here we've got objects that are either a cat or a croissant, and my machine learning algorithm wants to get a function which estimates which group it belongs to. It's the same type of problem. Right? I'm trying to draw connections between the images and the property of being a cat or a croissant. Just like I'm trying to draw a connection between being a graph and being a polynomial. Now, what mathematicians did is they built a model, much like we built that polynomial model for the Lorentz equations, which is the previous slide. And then they interrogated that model and said, okay, I've got this model that maps a graph to a cat, graph to a polynomial. What variables in that model actually matter? Right? So that's the partial differential equation that I'm plonking up there. If I see how much my model estimate changes as a function of different parameters of that model, different qualities of being a cat, I can see which ones sensitively change the prediction, and therefore those are the ones that are useful in making that connection. So I can do this, well, not me, but clever pure mathematicians can do this, and then they can deduce which properties of a graph are needed to make the prediction of the corresponding polynomial. Okay? So it's using traditional machine learning in a fairly straightforward way to get explainability from the model in a way in which the physicists, to be honest, with their ordinary differential equations, haven't really done, at least not successfully. And so this is actually work done by a bunch of people at various places, including a mathematician at Sydney Uni, Geordie Williamson, who's the third last author on that. Interesting paper, by the way. The more interesting stuff, which I started with my long preamble about how generative AI works, is how do we actually go beyond just making these predictive models and interrogating the parameters of these predictive models. So you've all heard, I assume, the idea that if I get an infinitely large room full of an infinite number of monkeys and give them an infinite number of typewriters, well, first you get a very bad smell, but once you get over that, one of those monkeys will eventually bang out the entire works of Shakespeare. Right? Just because the monkeys are smashing the keys, and just by random chance, eventually any given sequence of keys will be hit. The probability of it happening is quite low, but eventually it will happen. Eventually in a time greater than the length of the universe, but eventually it will happen. So what if we can make the monkeys kind of work a bit harder? So instead of just putting a room full of monkeys in front of typewriters and just hoping that they type something useful, what if we actually actively train them? And so monkeys here are obviously the large language models, the ChatGPTs. What if we, instead of just expecting it to spit out sentences, we show it what sort of things we would like to do? So one thing that we might consider doing is if we wanted to try to find solutions to a particular problem. Okay, that's very abstract. What do I mean? So there's another large group of mathematics problems that are all about finding better solutions to things. Okay, packing spheres in dimensional space, for example. Right? So what's the tightest configuration of oranges that you can stack and pack them as a group of spheres. This paper here is about a slightly different one, where the problem is if I've got like a grid of points, think of like a Go board, just a bunch of points, and I want to place a rock on particular points so that no more than 2 points are collinear. How many rocks can I put down there? With periodic boundary conditions for the mathematicians in the room. And so it's a difficult problem to do mathematically, but we can find solutions that satisfy those conditions. Right? We can find a solution on a Go board where I've put a bunch of rocks down and none of them are connected by straight lines, except for 2 at a time. And the question is, the mathematical question, the theorem is, what is the best you can do? So what these guys did, what these people did, is find a bunch of solutions to this problem, show it to a large language model, and ask it to come up with other solutions. Right? So the solutions here are arrangements of points on the grid, and it's just picking them at random based on having seen particularly good ones until it gets better and better and better. And they managed to show that they could actually outperform the current. They found new solutions. They found solutions better than any mathematician had found before. Right? Just by showing the computer mediocre solutions and hoping for something better. Finally, the kind of direction where I think all this is actually going, and what motivated me to think about this in the first place, is if we throw away the basic language models that we're thinking of in terms of natural human language, and we think about language as formal mathematical constructs, right? So just logical symbols that mathematicians use. Statements of if this, then this, right? And we train a model on those sorts of statements to build up larger and larger chains of those statements. We can test whether or not it's right. Okay? There's computer algebra packages out there that will tell you this is right or wrong. So if you get your language model spitting out logical constructs in mathematics, you can then feed it into something like, there's a package called Lean. You can feed it into that and it will tell you whether your answers are right or wrong. This is something you can't do with what ChatGPT spits out, because it's plain language text. So this is a team from Google did this, published in Nature quite recently. They've updated it with an improved version later this year as well. And what they did was they need to train the model, right? So they need to have a lot of mathematics to train it on, and this is the tricky part. So they construct a whole lot of axioms, conclusion, proof. So this is my assumptions. I have 2 right-angled triangles as depicted here, and this is my conclusion that I want to get to, whatever that conclusion is. These triangles are similar. C squared is equal to A squared plus B squared. And they construct a correct set of logical steps to get from the premise, the axioms, to the conclusion. Most of the things that they stick into the training are trivial, or at least not very long chains of thought, but they're chains of thought that make sense and are provably correct. They train the algorithm, the large language model, to process this, to generate sequences of these sorts of things. And then they ask it to, they construct a prompt, not in the way that you construct a prompt with ChatGPT by talking to it, but they say, given this axiom and conclusion, what is the proof? Right, so given this starting point, given this end point, you fill in the blanks for me. And they can check it to make sure that it works. And they gave this to, they gave this program maths Olympiad problems. So these are hard, pure maths problems from end of high school, first year university, basically, but the high school students doing this. They are questioned. Very often the people that perform well, and there's a high correlation, not perhaps causation, there's a high correlation between performing well on this maths Olympiad and going on to win a Fields Medal. Right, so these are really tough problems. But they're tough problems that don't require a whole lot of years and years of PhD level maths stuff. It's simple, it's straightforward geometry, right? And it got 25 out of 30 of them correct, which is not enough for the algorithm to get a gold medal, but it's enough for it to get a silver medal. Right? It's competitive with the very best high school students doing this stuff. Some of the calculations took a little bit longer than the time that the students were allowed to do the test. Sometimes it needed more than one go to get it right, but it got it right 25 times out of 30. And it's verifiable because there's a computer algebra package sitting behind it. So that was the last example. I just want to conclude with why I think this is interesting, and then give you a couple of final examples of where we are actually applying these type of ideas, not in mathematics, in other applications. So I think the idea of the optimization stuff, the finding good solutions to combinatorial problems like the points on the Go board, I kind of like this because I'm probably not going to offend anyone here because they're all in Auckland at the moment, but it's going to take a lot of the grunt work out of pure mathematics. Here is a complicated problem, find me a complicated solution to it from all the possible combinations. Right, the type of stuff that's just Sudoku on steroids. It's not really novel thinking, but it's just trying combinations until you get one right, and the computer can do it much better than we can. The second part of the stuff with using the language models to do things like proof geometry problems, I think that's where stuff is going to get really interesting. The big catch here, and I'm glad I've got two Pro Vice Chancellors in the room of research, because what we need is a lot more funding to make this happen. Training these models is extremely expensive. Unfortunately, it's like billions to trillions expensive. Well, at least billions anyway. These are the models that people like Google and Microsoft can train at great expense. So that's why the example I gave you here was from a group at Google. So they can afford to do these sorts of experiments. Us poor university professors, maybe not so much so, unless Andrew finds some deeper pockets somewhere. Let me just finish with 3 quick shout outs to other applications of this large language model stuff that we're already looking at. On the left is some work that we're currently doing with David's team at Integrated Energy, looking at rare diseases. So here, we're not interested in the corpus of proofs and statements such as that. We're interested in medical papers about specific rare diseases and scanning those specific rare diseases for information that might be predictive of symptoms, that might be predictive of treatments, and so on. The stuff in the top right, that picture is a very bad representation of the stuff that people like Mark Lindsay is thinking about doing the same type of thing in geology. Looking at the geological literature to try and build language models from that to suck the knowledge out of that. And finally, the natural language processing, technical language processing group. It's almost like I set this up to all the people in the room. That Melinda's group is doing, and Way's group is doing, on predictive maintenance that we did as part of the Data Science Transforming Maintenance Research Centre. And I will finish there with just one final quote to come back to the original statement from Alan Turing. And so Etta Dijkstra is a computer scientist, developed a lot of really fundamental algorithms in computer science, and has particular views on whether talking about machines thinking at all is even a sensible question to be asking. So thank you for your attention, and I'll take any questions.
So, Michael, fascinating. The whole time I had a smile on my face, you know. The first
I hope
thing
that's a good thing and not a bad thing.
Yeah, good thing. All good. I'm going to go first thing and read the Turing paper. So you got me interested in that. It's very interesting. Like you said, this is a vectorization of word. So where's the logical part coming from? If it's all prediction one after another, this is my biggest question. I think you answered it. I have to read the Nature paper. I saw that. So that's my first question. And the second one is explainability. As we know, it's more about local explainability at the moment. I haven't found a good way to provide a global explanation. Are you aware of anything? And I saw your paper. I have to read that. But yeah, if you have any answers to that.
So the short answer to both your questions is I don't know and no. The first question was where does the logic come from? And to some extent, it doesn't. Right? It's faking it. To the extent that it does produce logic, and people like Wei can jump in and correct me, to the extent that it does create logic, it's in the layers of the deep recurrent network, where you have different bits of the network are relating different constructs from different parts of your structure. But at its essence, it's just doing optimization. The second part of your second question was, remind me again?
Explainability, yes.
Explainability, yes. So the explainability, so I must admit, I put explainability there in there as a kind of a touch point to sort of just incite some questions. So thank you for asking a question about it. I guess I'm not using explainability in the full sense of explainability. I'm just thinking about it in terms of what can the model explain about the phenomenon with its modeling. Computer scientists talk about explainability of the model itself. Right? How do we know what the model is doing? That is something which I think we're a long way from having complete answers to, and which there's a whole nother avenue of stuff where we could be looking at applying mathematics to understand what's going on inside those network structures to try to get a sense of it. My default philosophical response is that this is all linear algebra on a digital computer, so it's not doing the same thing as your brain is doing anyway. So the way in which it's thinking, if you can call it thinking, is not the same either. So what it means to be explainable needs to be taken down a notch. It's not, I don't think it's about explaining the sentience of ChatGPT. I think it's about explaining ChatGPT's ability to find patterns.
It's just there's so many papers and they're talking about, explainable model, but we're far away from that.
Yeah, buzzwords. I think in many ways, many of the things that Andrew was talking about psychology, it's not a unique, they're not unique phenomena to psychology. Any other questions?
Why is it that figuring out cats and croissants and that problem is pure, like the pure, you said the pure mathematicians have figured this out, but extracting the equations for something like the system of Lorenz is squarely in our ballpark?
So think about it as trying to build a function between two categories. In the cats and croissants, I don't mean the cats and the croissants to be the two categories. I mean the two categories to be the images and the property of that image being a cat or a croissant. So I've got a bunch of images and I want to map those images over to the space of it's a cat or it's a croissant. In the same way that the pure mathematics problem is connecting particular graphs with particular polynomials in some abstract sense. So there's a theory that says that for every one of these graphs of this sort, we can construct a polynomial. There is a polynomial that corresponds to it. We don't know how to construct the polynomials. In the same way that I don't know, by looking at the pixels, how to decide whether an image is a cat or a croissant. But I build a model that can predict that it's a cat or a croissant, just as I build a model that can tell me what the polynomial corresponds to a particular graph is. And I then look at how that model varies with its parameters. and I can say, it's the fact that you've got this particular pattern of pixels that tells me it's a croissant rather than a cat, with probability. Is that your question?
Thank you.
Just don't ask me about technical language processing.
No, much easier. So you've had it's a fantastic slide, by the way. And I actually wasn't totally concentrating on your previous answer because I was looking at the slide. And I was just wondering, with all the events you guys have done this year, what do you think has been the most exciting development that you see that's relevant to us here at the uni? And what are you most excited about with data science for next year?
That's not fair. Well, personally, I was really chuffed to get Dr. Carl here for the day for the conference in the middle of the year. But actually, and this is going to sound like it was a staged question, in which case you should have got someone else to ask it. I think the program that we started running the data conversations, to be honest. So these, we started, thank you to Mike for hosting this at Kinetic IT's Buildings in the City. We had a group of around 30 invite-only senior executives from different organizations come to learn about large language models and technical language processing, and to realize just how much of an opportunity they have to take advantage of these sorts of things. And I think there's an opportunity to do much more of that sort of outreach to industry. The next problem is figuring out how to actually go from talking to them and getting them excited about problems to get them to fund them. But that's a longer discussion.
Thanks.
So I'll declare I'm a psychologist, although I'm feeling a bit seen at the moment. Look, I think it's a really interesting debate about whether AI models can think, and I think you've been quite provocative about whether it's a relevant question or not. But we're sitting here in a university that trains students. So I guess my question for you is, what do you think the future of university education is in a world of AI? And if we can't understand what distinguishes a human from a computer, how do we know how to train humans?
Let me start with the caveat that there's probably many people in the room that are equally good or better than me to answer that question, or have at least as many opinions on it as I do. First, I think there's been a lot of angst within the university about assessment, precisely because if we can't tell if it was generated by a human or a person, what do we do about it? And I think the answer to that question is, what are we actually testing if we're providing them something that they can use a machine to produce the answer to? In many of the same ways that in mathematics we no longer ask students to recite their times tables, at least not at university, because there's a calculator to do that for them. Right? It's a tool. And so we should be thinking about how we design our assessment so that we are assessing students on valuable critical skills that they can use. Because when they go out to the workforce, the boss is not going to say, no, don't use ChatGPT because it's not in the exam. Right? Their job is to use whatever tools they can to do something. There's a deeper part to your question about...
There is, because if a computer can think, I don't need a human.
So, yeah, I don't know. I know we're not there yet. I know that computers aren't thinking well enough to make us redundant. Everything that I've seen with generative AI requires an expert to guide it. If I was to try to pretend to be a clinical psychologist and rely on ChatGPT for my psychotherapy, I would have a higher failure rate than even Andrew credited me with. Just as I can't go and prove Fermat's last theorem by basic methods just because I asked ChatGPT, give me a hand. It still requires an expert to work with it. At the moment, it's only an assistant. In the future, I don't know. About a year ago, I was on record saying, "No, it's never possible because it's all just linear algebra and adding up numbers. It's no way it can actually think." I'm not 100% sure, but I don't think it's thinking yet. And I do think that in creativity, there is a huge gap. It can do some things incredibly well. You can ask it to compose a sonnet to describe quantum mechanics, and it will do a pretty good job, better than me. You can ask it to construct a sentence where the first word of each sentence is A through Z, and the sentence describes the plot of Hamlet, and it will have a stab at it. Sometimes it might get it wrong, but it will do something. But it hasn't got an original thought, and that's where there's still a strong claim for everything that a university does, from science through to humanities. Did that not answer your question sufficiently well?
You actually just started to answer my question, but
Oh, not the same question again? That was too hard.
no, I guess my question was around the ability for AI to come up with novel thinking, and do you think we test that on the human side as much, or do we credit humans for being novel when in fact they're doing the same thing AI is? They're rehashing old ideas in new ways.
Shortly after I finished my PhD, I was in Hong Kong, and there was a visiting Nobel laureate. Hong Kong likes to get those sort of people there to show off, and so he was visiting the department. Is Granger causality, and one of the things that he said was, don't talk about causality, I think it's rubbish, but that's beside the point. The other thing he said was, there's basically 7 or 8, I can't remember now, 7 or 8 original ideas, and we just keep combining them in different ways. I don't think that's quite true, but there's a large extent to which a lot of scientific innovation is combining existing ideas in different ways. And I think that counts as creativity. And I think that's what computers are particularly good at. They're not particularly good at knowing which ways are the good ways, but they're particularly good at trying to combine things in different ways, failing very often, and then presenting you with a few plausible things that might be good. The truly original stuff, the new direction and the renaissance of music, that kind of producing something truly different out of nothing that came before it. That's I believe, and believe is the word I'm intentionally using. I believe that's beyond what AI can do. Even if you look at things like the claimed dominance of AI playing Go, it really is just it was a combination of existing things in a way that humans wouldn't combine it. It wasn't a new way of playing the game. It didn't pick up the ball and run with it and create rugby.
Hi. From an industry perspective, I think the thing that we most worry about is the responsible use of AI and of generative AI. And, we can pretty much build a tool to solve any problem now, but I worry about whether we're overfitting to have a solution. I'm wondering if you have any ideas around governance or responsibility.
You're asking many questions there. The question, I'll focus on just the responsible AI. I guess there's 2 things that you need to think about: is responsible use of AI Right? So when students in the classroom are using AI to produce their essay, or when professors are using AI to mark those essays, is that responsible and appropriate and all that sort of stuff? Responsible use. And then there's the potential harmful consequences of using AI. Things like deploying automated self-driving in cars that then don't know how to identify a kangaroo because they were trained on antelope or moose, I think it was. A lot of that second stuff, it's complicated, but I don't think that it's genuinely new problems. It's more complicated because the algorithms are more sophisticated, but it's no different. The question about whether you can trust Tesla to not crash into a kangaroo is, I think, fundamentally no different than the question of whether you can trust a feedback control system to appropriately control the ailerons on the wings of an aircraft that you're flying in. There's traditional algorithms that we have similar trust in, and to a large extent, that's about building the verifiability is the wrong word here, but testing the algorithms well enough so that we do trust them. It's the trust rather than the responsibility that people seem to worry about. Does that answer some of your question? Your oysters are getting warm, so yeah. All right. I'll let Chow have the last word.
So, Michael, should we actually start by defining what we mean by think, and also related definition, like what do we mean by think, and being conscious and being creative, right? Because especially thinking and the consciousness are correlated, right? We know for sure computers or AI do not have a consciousness. For that, we can be safe because you need that to be motivated to eliminate humans, right? Right now, they're not doing that. But yeah, what do we mean by think? If we don't have a strict definition, we don't know whether you can think or not.
Well, that was what Turing said in the first place, right? It's like, what do I mean by think? I haven't defined think, and that's a whole nother event which the Data Institute will be organising next year, where we will invite the philosophy department along to come and debate the meaning of think. Yeah, look, I have a simpler issue, and that is with the way in which we use language around these algorithms in a way which imbues them with human qualities. Whether we talk about thinking or hallucinations, or a lot of these terms imply that this is something with agency and something with consciousness at some level, which I think is at least misleading, probably dangerous. I think Dijkstra's quote about it's like submarines, right? We don't care if a submarine can swim or not, but we know that it can go through the water quite effectively. So to some extent, we don't really care. Well, we do care because we're talking about it, but it doesn't really matter whether the machine is thinking by some definition of thinking. The point is it can do arithmetic, it can compose a poem for me, it can solve my control system problem for me. But the question really is it doing that? Can we test that it does do that? The question of whether it's thinking is, okay, I'll let Wei have the very last word.
Adding to that, thinking, I think, is how humans perceive it. I'm not sure whether people following the recent lawsuit of character.ai, the second lawsuit of teenager suicide, because they were talking to large language model supported characters, believe them to be true. And I think one of the characters basically said, come to me, come home to me, rather than come home to his parents. So that's the trigger of how that kid just committed suicide. Believing in the AI leading him to believe that his family don't love him.
Yeah.
So I think there's a very difficult problem here when we perceive large language model as some thinking machines or machines that actually can communicate with humans.
So, who, when they're talking to ChatGPT, uses the word please? Everyone put their hand down when you said that. Yeah, I mean it's a computer program. It's an algorithm. Yeah, 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 and no, and that's and stuff like the issue that you raise is where there's a really critical, dangerous issue here that needs to be discussed more, and that I think is my cue to stop talking and say thank you very much for coming along today and listening. And there is drinks, snacks, and oysters if they haven't completely, if they're still frozen. Cherie's got the health and safety declaration. If you want to have some oysters, please join us outside for further discussion.